Section 3 of Chapter 10 deals with the different types of solids. There are two main types of solids. You have an amorphous solid and a crystalline solid. Amorphous is disordered, and you can look at the picture and you can see there's no organization of the molecules within an amorphous solid. Crystalline solids have highly regular arrangement of their components. They're often ionic, for example, table salt. An example of an amorphous solid is glass. Now, crystalline solids can be further described by their structures, and there's a couple of different ways that we can look at the structure of a crystalline solid. One is by looking at the unit cell. A unit cell is a relatively small repeating unit that is made up of a unique arrangement of atoms and embodies the structure of the solid. So basically, you can break things down into a unit cell and it will still retain all of the properties and structure elements of a bigger unit. You can look at a crystalline lattice or crystal lattice, and that is the geometrical pattern of points on which the unit cells are arranged. You can also look at a space-filling unit cell, and that gives you a little bit more information about how the molecules are spaced and how they interact or don't interact within a unit cell. And there are a couple of different types. So you can have a simple cubic unit cell. In that situation, you have a atom at every corner. You can have a body-centered cubic cell, and that you have a atom at every corner and also an atom in the center. And finally, you can have a face-centered cubic cell, and there you have an atom at every corner. In addition, an atom at the face side of every side of the cube. And the next sort of thing to talk about is how do we know how these crystalline solids are arranged? And the technique is X-ray crystallography, also called X-ray diffraction. And I'll talk a little bit more about that in a couple of slides, but essentially it's a technique that provides information on the interatomic spacing and solid structure. William Henry Bragg and his son William Lawrence Bragg won a Nobel Prize in physics for coming up with this equation. So essentially, you can use a Bragg equation to determine interatomic spacings. You can look at the wavelength and the distance between the atoms and also the angle of incidence, which is the angle of a ray coming in, and the reflection, and get a lot of information from that. So let's look at a picture. The diagram shows two in-phase waves being reflected by atoms in two different layers of a crystal. The extra distance traveled for y on the lower wave is the sum of the distances between x and y and z, and the waves will be in phase after the reflection of a particular equation. Add some trig and you have the Bragg equation. So to say that in another way, you shine X-rays at a crystal and you look at the angle of reflection or deflection of those rays from the crystal. Here is another simplified way to look at X-ray crystallography. So the structure of crystalline solids can be determined by X-ray diffraction, looking at waves going into a crystal and looking between constructive and destructive interference within those waves. So essentially, you shine an X-ray through a crystal, those waves are diffracted in some particular pattern, and those pattern is picked up. You go through a series of computer fancy work, and you get a density of electrons that can be further turned into a model of the crystal or protein in this example. There are many different types of crystalline solids, and that plays a role into their properties. So for example, although sugar and salt both dissolve in water, the properties of the resulting solutions are very different because salt water will conduct electricity. So of the three different types of crystalline structures, you could have an atomic solid, and these atoms at the lattice points determine the structure of the solid, and an example of that is a diamond. You can have an ionic solid, and here you have ions at the points of the lattice that describe the structure of the solid, for example, sodium chloride. Or you can have a molecular solid. In this situation, discrete covalently bonded molecules are at each of the lattice points. And the example here is sucrose. Now, I will explain a little bit more in a bit about what I mean by discrete covalently bonded. This is a chart of the classification of solids. You can have atomic, molecular, ionic. Atomic solids are further broken down into metallic, network, and group 8A. And atomic solids are differentiated by the types of bonding that occurs within them. This chart is something that you will need to know. So I would spend some time with it. Section 4 goes into more detail on the bonding in metals. Metals are characterized by high thermal and electrical conductivity, their malleability, and also their ductility. These properties can be traced to what is considered non-directional covalent bonding found in metallic crystals. So let's talk a little bit more about that. Before we can get into specifics about the bonding in metals, we have to have an understanding about the structure of metals. So a metallic crystal can be pictured as containing spherical atoms that are packed together and bonded to each other equally in all directions. We call this closest packing, and that's a model that uses hard spheres to represent the atoms of a metal. The atoms are packed together and bonded to each other in all directions, and it's important that it's equally in all directions. So the example we did in class is if you had a box, a cubic shaped box, and you poured in a bunch of golf balls, the golf balls will layer directly on top of one another. But the layer on top will slide into the sort of dimple made by the first layer so that the two layers are offset a bit. If you then were to go through and take the golf balls out and put something else, let's say tennis balls in the box, they're going to fit differently because they're of different size. So the closest packing model talks about two different ways that spheres can be oriented. In an ABAB packing, the second layer is like the first, but it's displaced so that each sphere in the second layer occupies a dimple in the first layer. The spheres in the third layer occupy dimples in the second layer so that the spheres in the third layer lie directly over the first layer, and that's why we call it ABA. These have a hexagonal unit cell. You can also have an ABCA packing. In this situation, the spheres in the third layer occupy dimples in the second layer so that no spheres in the third layer lie above any in the first layer. And then the fourth layer would be like the first layer. I mentioned in the ABA model that it had a hexagonal closest packing arrangement. And so we can look at the unit cell of metallic atoms that would orient themselves in this way. And you can see that it's not your typical unit cell because it's not quite a square. You can also look at the cubic closest packing model, and if we were to look at the unit cell for something with a cubic closest packing model, we'd see that it's face-centered cubic. One of the things that's important and a characteristic of both structures is that each sphere has 12 equivalent nearest neighbors. So if we look at this red sphere here, it's equally touching 12 other atoms. Knowing the net number of spheres or atoms in a particular unit cell is important for many applications involving solids. So a cubic cell is defined by the centers of the spheres on the cube's corners. How many corners are in a cube? You have to think about how many faces are in a cube. And also remember that face-centered means an atom is stuck basically right in the middle of a face of one cube. And consequently, in the adjacent cube has the other half. So how many atoms would you have? Well, if you have 1/8 of an atom at every corner, and there are 8 corners, and then you have 1/2 of an atom on every face, and there are 6 faces, in a face-centered unit cell, you would have a total of 4 atoms. We went through an example in class where we tried to determine the density of solid silver given information about its radius. And for this, you have to remember that cubic closest packing means face-centered cubic. And you have to note that the structure of atoms touch along the diagonals for each face, but not along the edges. So we could put that together, and we could say, all right, we know that we have one radius in the 1/8 of an atom, 2 radiuses in the face part and then another in the other corner. And we could add that together and get something that looks like this. Then we could use a squared plus b squared equals c squared and get an equation for the distance of the side. There's a couple of models for the way that electrons bond in metals. Remember that metals conduct heat and electricity. They're malleable and ductile and have high melting points. And these facts indicate that bonding in most metals is strong, but also non-directional. And when I say non-directional, if you think about it, it's difficult to separate the atoms, but it's easy to move them around, provided they stay in contact with each other. So there are 2 models to describe the way that electrons would behave in a metal. The first one is the electron C model, and for this one, there's a regular array of cations, so the cations are evenly spaced, and they're sort of floating in a sea of electrons. Another model is the band or molecular orbital model, and here electrons are assumed to travel around the metal crystal in molecular orbits formed from valence atomic orbitals of the metal atoms. Finally, the last thing in this section talks about metal alloys. Metal alloy is a substance that has a mixture of elements and also metallic properties. You could have a substitutional alloy, for example, brass. In brass, a third of the atoms are copper. In brass, 1/3 of the atoms in copper have been replaced by zinc. Sterling silver is 93% silver, 7% copper. So substitutional alloys, some of the metal atoms are actually replaced by others. You could also have an interstitial alloy, and these are formed when some of the interstices, which is a fancy word for holes, in the closest packing metal structure are occupied by small atoms. For example, steel, carbon is in the holes of an iron crystal. And there are many different types of steel depending upon the percentage of carbon in the iron crystal. So that does it for the bonding in metals.